Ladies and gentlemen, this is Zhang from School of Computer Science and Technology, Huazhong University of Science and Technology. The paper I'm going to present is titled PopFetcher, the world's accelerated mixture of experts training via popularity-based Prefetch and which is co-authored with Chuanhu, Wang, Yuntao, Xiaofei, Liao, Haijing from Huazhong University of Science and Technology, Yuqing from Wuhan University, Yuedong from Fudan University, and Li from the Hong Kong University of Science and Technology. Transformer-based pre-trained language models such as BERT, GPT, and Llama have achieved remarkable success across diverse fields including natural language processing, computer vision, and machine translation. According to the scaling law, increasing model size consistently improves performance, driving the development of massive PLMs with up to trillions of parameters. Despite their enhanced capabilities, these large-scale models demand substantially greater computational resources, often encountering significant challenges in training efficiency and feasibility. In response to these challenges, the mixture of experts architecture has gained attention. Models like DeepSeek, Chen and Phi use multiple submodels within transform selectively activated by a gating network. This sparse activation allows scaling model capacity with sublinear training cost. Studies show MoE models match dense models' performance, making them a promising solution for efficient large-scale design. The mixture of experts improves large language models by using multiple expert submodels and a gating mechanism that dynamically routes inputs to relevant experts. This allows efficient scaling by activating only a subset of experts per input, reducing computation while maintaining capacity. In MoE, sparse layers replace traditional feed-forward layers in transform blocks. Each MoE layer contains several independent experts, usually feed-forward networks or more complex structures. A gating network assigns tokens to experts based on learned parameters, sometimes routing a token to one or multiple experts. This dynamic routing, trained jointly with the model, optimizes both performance and efficiency. Expert parallelism trains large MoE by distributing experts across multiple GPUs, overcoming single GPU memory and computation resource limits. Input tokens are dynamically routed to experts on different devices, requiring frequent cross-GPU audio communications to dispatch tokens and gather results. These communications are time-consuming and can significantly slow training. There are several advantages of applying AP. First, it enables training of MoE beyond single GPU memory, and it distributes memory and computation for better scalability. AP also allows parallel expert processing, potentially boosting throughput, but there are also some disadvantages. The frequent audio adds significant overhead, and the communication delays can greatly extend the training time. The dynamic token routing increases pipeline complexity and latency. Skewed expert activation in MoE causes hot experts to receive disproportionately high workloads due to the gate model's routing variability, leading to imbalanced token distribution. Early training shows variable token dispatching patterns that soon stabilize into localized activity with minor fluctuations. Although balanced gating mechanisms like capacity limits have been tried, some experts still consistently receive more tokens, resulting in heavier GPU loads on those hosting hot experts. This load imbalance is particularly severe in the early layers, highlighting the need for effective load distribution management to avoid overburdening GPU workers. In MoE training, each token undergoes audio communication twice per layer, dispatching and output collection, causing significant delays that can more than 50% of total training time for multi-workers. The primary bottleneck is synchronization, as expert execution and subsequent computations must wait until all tokens and their outputs are received. These issues caused by hot experts, whose heavier loads increase network contention and further slow synchronization. To address these challenges and reduce overhead, an efficient plan of AP is essential. To improve MoE training efficiency, one approach is to broadcast popular expert parameters across multiple GPUs to balance the workload and reduce skewed computations on overload workers. This allows specific tokens to be processed locally by replicated experts rather than being dispatched remotely, which helps lower communication overhead. However, while this approach is effective, broadcasting experts to all GPUs can introduce additional delay, potentially impacting overall training speed. An alternative approach is to pool expert parameters to the local GPU, reducing tokens transferred to remote experts. However, when the expert parameters exceed the input token batch, it falls back to original data flow. What's more, the limited memory makes it difficult to handle all the parameters when the model is scaling up. Imbalances in communication and computation caused by skewed expert selection significantly prolong MoE training. Existing solutions either push tokens to experts, which is called expert-centric, or pull experts to local GPUs, which is called data-centric, but both fail to handle uneven token dispatch inherent in MoE architectures, as they treat all data trunks equally and schedule them simultaneously, causing blockages during large data transfers. We propose a hybrid push and pull strategy that combines the advantages of both methods by adapting data transfer based on token and expert parameter volumes after gate-based token routing. If token volume exceeds expert parameters, tokens are sent to experts. This method includes expert prefetching, also includes expert prefetching to enable advanced retrieval of remote experts. Under that theme, two computation patterns are considered: local computation, where tokens are sent to specific experts and results returned, and prefetching computation, while experts are fetched locally to avoid sending tokens over the network. Prefetching requires an extra step during the backloop pass to send gradients from replicated experts back to the primary located worker for global reduction, necessitating gradient synchronization that consumes network bandwidth and must be factored into prefetching decisions. Non-MoE components between MoE layers offer optimization opportunities despite challenges. The figure above shows that during non-MoE computations such as the attention layer, workers use only local input data, causing network links to be underutilized. As training progresses, expert load variations stabilize, allowing historical token distributions to guide expert prefetching. By proactively fetching popular experts from the remote GPUs to local workers before selection, future all-to-all communication overhead can be reduced, effectively leveraging slow network links to enhance communication efficiency. However, several challenges approach in the practice of hybrid paradigms. The first one is how to accurately predict the popular experts in the next MoE layer, because load distribution changes dynamically during training. The second is how to prefetch appropriate experts within worker capacity, as GPU memory is limited and multiple experts may already reside locally. Then is how to manage extra costs of expert prefetching, as synchronization arises to ensure experts are ready before the next forward pass. In this paper, we present PopFetcher, an advanced MoE training system with popularity-based expert-wise prefetching to decrease all-to-all communication overhead and ensure balanced GPU workload. PopFetcher is primarily composed of three key modules: routing information collector, a prefetching decision maker, and asynchronous scheduling executor. We will delve into a dynamic prediction for expert popularity, which is deemed to be both lightweight and accurate to enhance expert prefetching. Here are the main notations we use in our paper. There is a correlation in expert selection across consecutive MoE layers, where the pair of experts chosen reflects this relationship. The figure illustrates the conditional probability of selecting given the previous result, revealing the distinct patterns and common correlations that enables predicting the next layer's hot experts based on the previous layer's choices. Although the popularity and correlations involve gradual during training, this slow change supports the effectiveness of early expert prefetching outside MoE computations. To address dynamic prediction while minimizing impact on normal training, we propose a sliding window-based prediction to pinpoint hot experts. Initially, we analyze the distribution of tokens of recent iterations. The first formula is the popularity of the current MoE layer. Here, S represents the size of the sliding window. Let M signify the total number of tokens. Denote the ith expert on the J's layer as EIJ. We can modularize the correlation between experts. Finally, the expert popularity based on the correlation is given. First, we consider the conventional case where prefetching is excluded, which can guide later analysis of our system. Let BW denote the number of tokens received by worker W, which is the first formula, where the number of tokens from worker N based on expert popularity predictions is calculated as the second formula. The two full connecting layers in MLP accounts for 3 GMM operations and 4 rounds of all-to-all communications, including both forward and backward paths. The training latency of worker W is given by the third formula. Expert prefetching consists of 2 delay types. The first is prefetch expert computation, and the second is model gradient reduction. We derive the training latency under expert prefetching. Our goal is to minimize the end-to-end latency, which is the minimum of the last formula over all workers involved. The main challenge in expert prefetching is the large search space for selecting next layer experts. We address this by expert pruning, which significantly reduces the number of experts to search. We set conditions below. The first is GPU memory limitation, and the second is transfer time constraints. Moreover, expert prefetching for any worker is supposed to reduce end-to-end latency. The GPU cluster featuring heterogeneous link bandwidths. Intra-machine GPU communication uses link up to, and the GPU to CPU links use PCIe, where data moves from link to CPU memory and then to GPU via PCIe. Workers prioritize fetching experts from higher bandwidth sources, sharing internal experts through CPU memory to avoid external overhead. This scheduling scheme retrieves experts over the fastest links, leveraging CPU memory to minimize redundant transfers and enhance communication efficiency. The expert prefetching replicates experts across workers, necessitating extra R reduce during the backward pass, typically all-to-all for EP, R reduce for non-MoE layers, and R reduce for prefetched experts run in separate CUDA streams. Without careful scheduling, these concurrent streams compete for limited network bandwidth and GPU resources, disrupting backward computation. Ideally, all-to-all communication should have strict priority to reduce bandwidth contention, with all-reduced tasks launched preemptively and all-to-all allowed to preempt the GPU. However, optimized multi-GPU communication libraries like NCCL fix communication primitives to CUDA streams upon invocation, preventing dynamic scheduling or resource reallocation. To address this, communication operations are decomposed into pipelined micro-operations. By interleaving micro-operation, network idle times are fully utilized while GPU workers remain busy, improving overall efficiency. We have developed the PopFetcher atop PyTorch. We implemented it as a PyTorch plugin that can function independently or be integrated into the Megatron LM framework. We compare our PopFetcher with the following frameworks: DeepSpeed, Faster MoE, MegaBlocks, Tudo, and Genus. We evaluate PopFetcher on two GPU clusters. Cluster A comprises two machines, each outfitted with 4 NVIDIA RTX 4090 GPUs that have 24 GB of memory per GPU. The GPU nodes are connected through a 100 GB per second IB for communication. Cluster B includes 8 machines, each equipped with 4 A10 GPUs, totaling 32 GPUs, with each also featuring 24 GB of memory. The internode bandwidth is 32 GB per second. We test PopFetcher on two MoE settings, the MoE GPT model and the MoE BERT model. PopFetcher speeds up MoE training by prefetching popular experts, reducing per iteration time. To ensure training equivalence with traditional MoE, we add a reduction step to synchronize greetings between prefetch and original experts. We validated this by training MoE GPT on cluster A using both faster MoE and PopFetcher. The figure shows loss curves for naive Topk and G-sharp routing. Results confirm that PopFetcher preserves expert selection and convergence without extra steps, achieving statistical equivalence and maintaining model accuracy. The figure 11 shows PopFetcher's speed up over baselines across GPU clusters, measured against the slowest system in each setup. PopFetcher improves training speed by 1.28 to 2.4 and 1.18 to 18.3 in the two clusters, respectively. Genus, which pulls all expert parameters, demands high GPU memory and often causes out-of-memory errors, so it is excluded from the figure. We continue assessing the benefits of expert popularity prediction and backward stream scheduling by comparing PopFetcher with baseline MoE training methods that use random expert prefetching or default stream strategies, which overlook expert selection and stream priority variations. The results show that our method achieves 1.3 and 1.26 faster training, and the pipeline stream scheduling cuts down iteration time by another 10% ratio. Furthermore, we assess the prefetching status of experts in MoE GPT and MoE BERT models. The vertical axis shows the global index of experts, and the horizontal axis represents iterations. Darker cell colors indicate more frequent prefetching. Results illustrate that strategic prefetching of certain experts can speed up training. PopFetcher combines the strengths of traditional data-centric and expert-centric through a hybrid approach of sending tokens and plotting experts. When compare its training throughput and per iteration time with data-centric framework, which is genus, and expert-centric, which is without prefetching. As shown in Figure 15, experiments on cluster A with MoE GPT and MoE BERT models demonstrate that PopFetcher outperforms both paradigms. By prefetching popular experts, PopFetcher ensures a more balanced workload distribution across workers, since the loads of hot experts are shared among multiple workers. In this paper, we propose PopFetcher, a scalable MoE training framework that reduces auto communication bottlenecks by leveraging popularity-based expert-wise prefetching. PopFetcher detects skewed and correlated expert selection patterns using sliding window prediction to estimate popularity in upcoming layers. It then optimizes expert to GPU mapping based on end-to-end training latency, minimizing communication overhead and balancing workload. Additionally, PopFetcher overlaps or reduces with non-MoE computation during network idle times to accelerate the backward path. Experiments show that PopFetcher reduces training time by 15% to 94.5%, outperforming the state-of-the-art systems. This is the end of my presentation. Thanks for listening.